Right, here we have a hexagon, A, B, C, D, E, F. So that's that sort of arrow shape there, which does have 6 sides, so it is a hexagon. And what are we told? Well, we're told that these two things, so that's the two halves of the hexagon, B, C, D, E, or C, B, E, D as they call it, and A, B, E, F are congruent parallelograms, which basically just means that, in this case, B, E is a line of symmetry. Okay, and we're told also, and let's put this on the diagram, that AB, that's this side here, is equal to BC, and they're both equal to X centimeters. Okay, so X and X there and there. What else does it tell us? Well, it tells us that P is the point on AF. So there's P, and it's the point on AF. And Q is the point on CD, such that BP, we better draw these in, BP, there it is, equals BQ, and they're both equal to 10. All right, this diagram is getting quite complicated already. We're also told that, I'm just going to change colour here for clarity, that ABC, that's the red angle in there, is 30 degrees. Okay, and we're asked to prove, oh my word, prove something hideous about cos of PBQ. Well, which is the angle PBQ? This angle here is PBQ. Let's give it a nicer name. Let's call it theta. Okay, so we're asked to show that cos theta is that hideous mess there. Now, this diagram, as I say, is getting quite complicated, and there are clearly two sort of overlapping things going on. We've got the triangle ABC, which we've got two sides and an angle of, and we've got the triangle PBQ, which we also have two sides and the angle we're working with. So let's draw these things separately. Right, so let's go with ABC. Here it is. I'll just draw in the line AC. I haven't actually on the diagram, but there it is. Okay, so ABC has a 30-degree angle there, and that is X and X. Okay, and then let's draw PBQ, which looks like this. There's P and Q, B at the top. That's the angle I've called theta, which is the one we're working with, and we know that these two sides are 10 centimeters. Right, how are we going to work out a relationship between theta and X? Well, there must be something linking these two triangles, and sure enough, look, AC and PQ on my diagram, I didn't draw PQ in, but I could have done, are equal, because of course we've got parallelograms. So AF and CD are parallel, and those two sides I've just indicated, the two remaining highlighted ones, are equal. Let's give them a name. Let's call them Y. And now you'll see that we've got Y on both my triangles down at the bottom here. So if I can use this triangle to find an expression for Y, and then put it into this triangle, I'll be able to link the two things together. So let's try that. Okay, so looking at the options we have available, well, what's going on? We've got a non-right angle triangle here. We have an angle and 3 sides to work with. And if you look in my blue box up here, there are lots of options, but the one with 3 sides and an angle is the cosine rule. So let's use the cosine rule on that triangle. Okay, so first thing we need to do is make it look a little bit more like this triangle here. We're trying to find an expression for a squared, so let's call y a, which means we are going to have to relabel. So if that's little a, then the side at the top, the angle at the top is big A, and I need to call the angle down the bottom left here B. We can leave the C where it is and label the sides opposite them, little b and little c. So, using the cosine rule on this triangle, let's put in what we've got. Well, we've got a squared, so that's y squared, is equal to b squared, which is x squared, plus c squared, which is also x squared, minus 2 times b times C times cos A. And A is 30, is it not? Okay, so let's sort this out a little bit. So I've got y squared equals, well, x squared plus x squared is 2x squared. And then I've got minus 2 times x, which is also 2x squared, but it's multiplied by cos 30. Now, cos 30 is one of those things you're required to know. All right, you should know that cos 30 equals root 3 over 2. I've just written it down at the top there for you. How might you remember that? Well, if you remember the old 30, 60, 90 triangle, like this, okay, and the only thing you have to remember in that is that sine 30, so the opposite over the adjacent, the opposite over the hypotenuse, is a half, a little bit of Pythagoras, and that's root 3. That's difficult, but it's a way of remembering it. So, cos 30, back down to the bottom here, is root 3 over 2. Let's do a little bit of cancelling. There's the green cancelling pen. Well, the only thing I can cancel is the 2 in the second term with the half. So that's good. And then, because I can see sort of what I'm going for in the question, and there's something factorised here, not quite sure what it is yet, but I'm going to take the x squared out of this expression. And look, if I take the x squared out of each of these terms, what have I got left? I've got 2 from the first term and just minus root 3 from the second term. And I sort of feel as though I'm going somewhere in the right lines here because, look, x squared times 2 minus root 3 appears in the answer that I'm going for. So that's very encouraging. I'm not even going to square root now because actually I can see that in the other triangle, which I'm just going to move to give myself a bit more space. I know you can't do that. Oh, I've left a bit behind. Look, there we go. Is also going to have something to do with y squared because I'm going to use the same rule. I'm also going to use the cosine rule in the second triangle. Let's again relabel this triangle with an A at the bottom. So get rid of the B at the top and call it A. And then let's just replace P and Q by B and C so that it fits the cosine rule formula. So let's go with the cosine rule again. Now this might look quite similar, but let's see what happens. So y squared, or my second triangle, is equal to, this time, b squared plus c squared is 10 squared plus 10 squared, minus 2 times 10 times this time cos theta, or remember that I've called the angle PBQ theta, so that's fine. And sorting this out, we get y squared equal, well, 10 squared is 100, plus another one is 200, and then I've got minus, well, 2 times 10 is also 200, and that's times cos theta. And now, if you have a look at this, well, actually, let's just factorize this as I did with the other one, and take the 200 out, and I get 200 times 1 minus cos theta. And now, looking at these two expressions, they're both y squared equals, and so actually I can just make the right-hand sides equal. All right, so let's bring these two things together. Let's give myself a tiny bit more space down the bottom here. All right, so we can say, so here we go, x squared times 2 minus root 3 is equal to 200 times 1 minus cos theta. And that's, have I done that? Well, I've just essentially made these two things equal. Okay, so what do? Well, all we have to do now is get cos theta equals. So let's divide by 200 to get rid of the 200 on that side. It also starts to make it look like what I'm going for. Keep an eye on what we're going for here. The 200s cancel on the right, and I've just got 1 minus cos theta equals the big fraction on the left, and look at the big fraction there. The big fraction is the same as that fraction there, but with a minus sign, obviously. And a little bit of jiggery-pokery here, adding the cos theta to both sides and subtracting the fraction from both sides will give me exactly what I want. So let's just write that down. I'm going to add the cos theta over here, and I'm going to add the cos theta over here, which gives me cos theta plus, I'm just going to write this as it's written in the question, 2 minus root 3 over 200 times x squared is equal to 1. And then all I have to do is subtract the fraction from both sides. Okay, so minus the 2 minus root 3 over 200 x squared from that side, and subtract the 2 minus root 3 x squared over 200 from that side, and I really have got what I'm asked for. Cos theta is equal to 1 minus, and there it is, 2 minus root 3 x squared over 200. And we're done. All right, that isn't easy, but it is possible. And if you go back and have a look at it, all we've done is we've used the cosine rule twice, but we've had to be very careful.